Okay, good morning, everyone. First, we have Dr. Erez Berg as our first lecturer. Please, the floor is yours.
Okay, thank you very much. Welcome back. I'm going to switch gears a little bit and still talking about the multi-layer graphene system, but a very different one. I'm going to talk about rhombohedral multi-layer graphene. So it's still a stack of graphene layers, but unlike yesterday, there's not going to be any twist angle. Um, and it has some interesting similarities to the twisted system, but many differences. And I'm going to talk about superconductivity in this system that is very interesting and still not understood. So just as a brief background, I think we're living in a very interesting era in 2D materials in general, right? So there's a huge phase space that's been sort of exposed in the last decade or so of new 2D correlated electron systems, and they're very, very diverse. So you saw twisted bilayer graphene earlier in the school, and I'm going to talk about rhombohedral multilayer graphene. Same graphene, so the basic building block is graphene, but you can really think about that as a different material. And there's also the multi-layer TMD systems that are also 2D electron gas that show a huge variety of correlated electron phenomena. So one way to think about all these systems is sort of generalizations of the textbook problem of the homogeneous electron gas, right? If you think about the Gellium model that you see in sort of first course in solid state physics, but with added features. So instead of just a plain vanilla sort of parabolic electrons in a 2D plane with a parabolic dispersion and two spin flavors, you have multiple valleys in all these systems. You have anisotropic dispersion relations. You can have a superlattice like a Moiré lattice. You can have Berry curvature in these bands and so on. And as a result, you get phase diagrams that are much richer than the phase diagram of the plain vanilla homogeneous electron gas. Okay, so we talked about all kinds of generalized ferromagnets. If you have a lattice, you can also get Mott insulators. You can get superconductivity. You can get Chern insulators, either integer or a fractional, and so on. Okay, so really a vast phase space to look for, and I think the field is really looking for sort of ideas of how to treat all this rich physics, both theoretically and experimentally, and sort of a guiding principle to look around in this phase space. Okay, so I'm gonna talk about superconductivity in particular in these systems. So rhombohedral multilayer graphene. So a bilayer and trilayer, and it turns out that it extends to n layers, and we think that all of these can be thought about as one phenomenon. I'll talk about the open problems in the question, in particular in this field. In particular, what's the mechanism, what's the symmetry of the order parameter, and I won't have answers. I will just try to give some considerations. And finally, if I have time, and I most probably won't, I'll talk a little bit about spin polarized triplet superconductors that are also very prevalent in these systems. Okay, so that's by itself is interesting. Okay, we don't have that many so clear and clean examples of triplet superconductors, and they definitely occur in these systems. And I'll talk a little bit about what new physics might arise, which is sort of special to these triplet superconductors. As always, please interrupt me at any point with any question. Okay, so a rhombohedral multi-layer graphene. Okay, so what is that? So here are some pictures. So you stack multiple layer of graphene. It's basically a thin sheet of graphite, which is nothing but a stack of graphene sheets. Okay, and if you think about stacking two graphene layers on top of each other, the way it likes to stack is in this so-called AB or Bernal structure. where the A sublattice of one layer is on top of the B sublattice of the other layer. Okay, so that's the thermodynamically stable stacking. If you add a third layer, now there are actually two options. Okay, so the ground state of the system is the so-called ABA structure. Okay, so you go from one layer, then the next layer has its A sublattice on top of the B sublattice of the bottom, and then the third layer is actually registered with the bottom layer. Okay, but you can have a metastable state, which is very, very close in energy, which is the so-called ABC structure, okay, which continues in this kind of staircase fashion. Okay, the thermodynamically stable one would be shifting this layer over here, such that the A3 would be right on top of the A1. Okay, so that would be a graphite, and this is the ABC or rhombohedral stacking. Okay, just to make sure we're all on the same page. Okay, what is this picture? So every graphene sheet has 2 atoms per unit cell. This is just a side view of the unit cell. Okay, and what's pictured here is a side view of the unit cell of the trilayer. Okay, is that clear? Okay, so this slight stacking. So this is basically a stacking fault in graphite. It occurs naturally. So if you take a piece of pencil, you would find that you would get these regions where you have this kind of wrong stacking, and it's metastable. It's very, very close in energy, so it occurs naturally. Okay, but this slight difference in stacking makes a huge difference to the low energy electronic states. Okay, so to the extent that as far as the low energy physics is concerned, this is a different material than the Bernal stacked ABC graphene. Okay, and by the way, you can extend this to any number of layers. So you can have A, B, C, A, B, C, and so on. And these actually occur. Okay, when you just exfoliate graphene, you get all kinds of stackings, and in particular, it's less common than the Bernal stacking, but you would find n layers of this rhombohedral graphene. Okay, and what's interesting about this stacking is coming from this geometry. Okay, so I highlighted the shortest range hopping that you would expect on this kind of lattice. So of course there's the in-plane hopping in every graphene sheet connecting the A and B sublattice, but there's also the interlayer hopping, which is smaller, maybe by a factor of 10 or so. Okay, but if you're sitting close to the Dirac point of graphene, you know that at the Dirac point, the A and B sublattices are degenerate. Okay, this is precisely the level crossing that you get from the Dirac dispersion. And then what would happen is that the interlayer hopping would actually hybridize and gap out, push away from the Fermi energy, these B1 and A2 sites, the B2 and A3, leaving at low energy only the states at A1 and B3. Okay, so what you get, if you extend this to more and more layers, close to zero energy, what you actually get is surface states that live on these 2 sublattices, the A sublattice of the bottom layer and the B sublattice of the top layer. Now, moreover, you can then easily see that if you apply a displacement field, just an electric field perpendicular to the system, you actually split these 2 states in energy. Okay, so that opens a gap at zero energy. And interestingly, what you get is that the dispersion of the resulting conduction and valence band is very, very flat as a function of momentum. Okay, the reason it's very flat is that it's hard to hop. It's basically in the plane. You have to go through these states that are off resonant relative to zero energy. Okay, and it's kind of a fun exercise. If you solve this exercise of just this tight binding model on this type of lattice, what you would find is that without the displacement field, a low energy dispersion of the 2 bands originating from the 2 surfaces actually scales like k to the power n, where n is the number of layers. Okay, so you know that for n equals 1, that's graphene, that's linear dispersion. N equals 2 is Bernal bilayer graphene. There the band touching is parabolic. And it continues. For a trilayer, it would be k to the power 3. and k to the power fourth and so on. Okay, so the precise power law is somewhat of an artifact of the nearest neighbor hopping model, which is not quite correct. So the dispersion would look more complicated, but the trend is correct. So you get more and more flat dispersion as you go to a higher number of layers. Okay, and moreover, if you apply a displacement field, you open a gap and the dispersion becomes even flatter at the bottom of the conduction and top of the valence band. Okay, so this very, very interesting electronic structure is the driver of all the interesting physics that I'm going to show. Okay, so let me show some pictures. The states are originating from these top and bottom layers. Okay, you can write an effective two-dimensional Hamiltonian. Okay, the original Hamiltonian for tri-layer would be six-dimensional. Okay, because 3 layers times 2 sublattices per unit, 2 sites per unit cell. You can write the effective low-energy Hamiltonian just of the bottom A and top B, and that would look like this. Okay, so that would have this cubic dispersion term connecting the A of the bottom and the B of the top. Okay, and delta 1 is a term which is proportional to the displacement field. That's the energy offset between the A1 and the B3. Okay, and gamma is a term that would give you the trigonal distortion of the trigonal warping coming from the underlying lattice. Okay, so what if you just solve this 2x2 Hamiltonian? What that would give you is a very, very flat conduction band, very flat valence band, and then at some momentum scale they start to disperse. Okay. This is what the density of states, this is a cut through the dispersion close to one of the valleys, say the K point. And this is the corresponding density of states. Okay, so the black curve is zero displacement field. So you see this band touching. Instead of a cubic band touching, you actually get 3 Dirac points. This cut is cutting through one of them. The blue curve is what happens when you apply displacement field corresponding to an energy difference of 20 millivolts between the top and the bottom. And you see the gap opening, and you see this very, very flat dispersion at the edges of the two bands. Okay, and this flat dispersion corresponds to a huge peak in the density of states. It's this peak, of course, that would give rise to interesting physics. Okay, so it's an interesting contrast with the case of a Moiré lattice, like twisted bilayer graphene. Okay, so here, it's not that we have a flat band. The entire band is actually very dispersive, but there's a region in momentum space, like a little disk in momentum space, where the dispersion is very, very flat. Okay, and as you partially fill this flat region, you expect correlation effects to be strongly enhanced. Okay, this is what the Fermi surface looks like on the whole side that I'm going to talk about a little bit in more detail. So this is putting the chemical potential somewhere here. And this is what the density of states looks like now as a function of density. And also pictured here is the Fermi surface. So at very low density, there are actually 3 pockets because of trigonal warping. So these 3 small pockets are basically the top of this dispersion over here. These pockets, as you add more and more holes, these pockets expand, and at some point they touch each other. So there's a Van Hove singularity. Okay, this is a log divergence of the density of states, as smeared by some parameter, this calculation. And then there's a region of density where the Fermi surface is an annulus. Okay, so there's an outer Fermi surface of holes and an inner Fermi surface of electrons. It's basically a Mexican hat-like dispersion. It's just cutting through this region. And then ultimately, when you fill more and more holes, the inner pocket disappears, and you recover a sort of simply connected single Fermi surface per valley per spin. Okay, so interesting evolution of the fermiology, very non-trivial, okay, very non-parabolic dispersion, including this Van Hove singularity. And of course, the question is, what happens if we tune the density somewhere in this region? Okay, so we have a high density of states, high effective mass. We expect some correlation effects to become dominant. And this is indeed what happens. Okay, so this experiment was done by Andrea Young's group, UCSB. Okay, so this is ABC tri-layer graphene, and this is an experimental phase diagram. Okay, so let me walk you through that. Shown here is the phase diagram at very low temperature as a function of both electron and hole filling, okay, both positive and negative electron density and displacement field. Okay, so the phase diagram depends very crucially on the vertical electric field, and the quantity that's plotted here is the inverse electronic compressibility. Okay, so it's basically capacitance. This is a capacitance measurement. So it's measuring how many electrons are going in and out of the system when you modulate the gate potential. Okay, and the first thing that jumps at you is that at finite displacement field, you see these very sharp features that depend on both density and displacement field. These are actually phase transitions. Okay, so this phase diagram is actually mapped in great detail. Okay, so it turns out that what's happening between these different regions separated by sharp transitions is that the system is undergoing symmetry breaking transitions. Okay, so out here, when you're far away from the flat region of the dispersion, you fill in electrons, they go equally into the four flavors, the two spins, two valleys of the system. But as you approach the peaks in the density of states, the system tends to break that symmetry and choose only two out of the four flavors and fill only these. Okay, and as you tune the density even lower, the symmetry breaks further and you choose only one of the four flavors and fill only that one, and so on. Okay, and a similar evolution occurs on the electron side. As you see, the details are different, but qualitatively similar. Okay, so the physics is exactly what we discussed in the context of twisted bilayer graphene. Okay, so these are Stoner-like transitions, presumably. They're driven by exchange interactions. You can gain a lot of exchange interaction by polarizing in spin and valley space. Okay, and you lose kinetic energy, but when the bands have such a high density of states, you don't lose as much. Okay, so this is the energetic consideration. This doesn't happen when the density is far out here, because there the density of states is small. It happens close to these high density of states regions in the dispersion. Okay, so how do they know all of this? Well, this phase diagram is mapped in great detail using Shubnikov de Haas oscillations. Okay, so what they really track is the fermiology. So you do Shubnikov de Haas. From that, from the frequency of the oscillations as a function of magnetic field at fixed density, you can read off the areas of the Fermi surfaces in momentum space. Okay, and they've done that in exquisite detail. Okay, so this is a very clean system. The mean free path is enormous. So you really see quantum oscillations down to quite low fields, okay, 0.1 or 0.2 Tesla. And you can really map out the evolution of the Fermi surfaces in great detail. So this is what they infer. This is for the whole side. Okay, so what they really see here, out here in the 4x region, what they see is that there's a single frequency. And if you want to match that frequency, which is an area in momentum space, if you want to use the Lantiger volume law and match that to the total density of electrons, you have to multiply by 4. Okay, so this means that every Fermi surface is fourfold degenerate, which is exactly what you expect in the symmetric state. And then once you go to this region number 6, you see actually two frequencies. Okay, and the two frequencies correspond to the inner and outer Fermi surface, and each one of these Fermi surfaces is fourfold degenerate. And you can track the evolution of these Fermi surfaces as a function of density, and from that you can know that one of them is electrons and the other one is holes. Okay, and then in this region number 5, you see just one frequency, but you have to multiply that by 2 in order to match the full density, and that means that each Fermi surface is only doubly degenerate, and so on. Okay, so this way you can really map out this evolution. you can write down a very simple-minded model where you have 4 flavors with exchange interactions and just assume rigid band shifts as a result of exchange. And you can actually understand quite a few of the structure, quite a lot of the structure of this phase diagram from this very simple-minded model. Okay, this is somewhat reminiscent of the physics in twisted bilayer graphene, even though, of course, the details are very different. Okay, so it turns out that as you walk around this phase diagram between all these symmetry broken states, there's actually superconductivity hiding. Okay, so it's an electron gas. Sometimes it's an electron gas with all 4 flavors present. Sometimes it's an electron gas with some flavors full and others missing. And it turns out that it's the same electron gas that actually becomes superconducting. Okay, so here's the same phase diagram on the whole side, but now it's transport. Now it's the electronic resistance as a function of density of holes and displacement field. And you see that at the boundary, okay, so this different contrast is the boundary between 2 of these phases. One of them is symmetric and the other one symmetry broken. You see this region, this light blue corresponds to zero resistance. So this sliver here is actually a superconducting state. Okay, and there are actually 2 superconducting regions here labeled by SE1 and SE2. This is ABC trilayer. It's not special to the trilayer. Okay, so this is an experiment on bilayer graphene with different substrate, WSE2. And you also see these different superconducting regimes. And it turns out that superconductivity actually occurs in lots of these systems. So also Bernal bilayer graphene on HBN, a substrate. It turns out that here something interesting happens. Superconductivity only occurs if you apply an in-plane magnetic field and not without, which is very unusual. It also occurs when you put ABC graphene on a WSE2 substrate. It occurs with basically any numbers of layers as long as it's in this rhombohedral stacking. Okay, so recently there have been experiments in 13 and 15 layers. And of course, the phase diagram looks very different. Okay, but there still is superconductivity also in these systems. What's common to all these rhombohedral stacking systems is that the electronic states are always coming from the surfaces. Okay, they're always localized. There are 2 bands localized on the top and the bottom surfaces. Okay, so lots of superconductivity, and many details are different, but some things are common. Okay, so here's some properties of all of these superconductors. TC varies. Okay, so TC is the lowest ones would be around 40 millikelvin. Of course, these are not really the lowest ones. These are only there are probably ones with even lower TC that we can't observe. But TC can go all the way up to close to half a Kelvin, 400 millikelvin. The record, to my knowledge, belongs to ABC graphene on WSE2 substrates. That's around 400 millikelvin. Okay, so there's a difference that the substrate makes. Okay, what you put the graphene on top of, you encapsulate the graphene in some sort of insulator layers. And what that insulator is actually changes the properties of the system. So there's a difference between, there are 2 types of substrates that are used. One of them is HBN, the other one is WSE2. The WSE2 induces spin orbit coupling into the graphene. Graphene itself has a very small spin orbit coupling, but when you put it on WSE2, the electrons tunnel into the substrate, spend some time there, and they inherit some of the spin orbit coupling from the substrate. So that's very useful. You can tune spin orbit coupling in and out of this system and see what it does. Okay, in some systems like the ABC graphene, spin orbit coupling actually enhances superconductivity by quite a bit. Okay, by a factor of 3, enhances TC. But the interesting thing is that if you have HBN substrate, there's very low spin orbit coupling in the system, basically just the native spin-orbit coupling of graphene, which is present but not very big. And then you can ask, well, what happens if I apply an in-plane magnetic field? Okay, so that's mostly the Weizmann effect. And the question is superconductivity killed by Weizmann field? And the answer is sometimes it is and sometimes it isn't. Okay, so for instance, for ABC graphene on HBN, there are these two superconducting phases, okay, SC1 and SC2. SC1 more or less obeys the Pauli limit, meaning when the Weizmann energy is comparable to twice Tc or so, superconductivity is killed. SC2 doesn't obey the Pauli limit. It actually violates that by a huge factor, at least 10. Okay, so this has a tiny, tiny out-of-plane critical field of a few millitesla or 10 millitesla, but the in-plane field is at least a Tesla and probably more. Okay, so that suggests that when we don't have a lot of spin-orbit coupling, we can distinguish sharply singlet and triplet superconductivity. And it turns out that in these systems, you can get either a singlet or a triplet superconductor, depending on where you are in the phase diagram. So that's already interesting. Another common feature of all of these superconductors in these different systems is that they always occur either near a phase transition between two symmetry broken states or inside one of the symmetry broken states. Okay? So for instance here, this is very, very apparent. Okay, so this phase over here is the symmetric phase. It's a phase where you occupy all four of the flavors equally. This phase over here is a phase where you broke that symmetry and occupy only two of the four. Okay, so and it looks like the superconductor is living right at the border between these two phases. It's actually on the symmetric side in this case. Okay, so the superconductor lives in the symmetry unbroken phase, but right on the border to the ordered phase. Okay, and these phases always have this character. They either live right at the border between two symmetry broken states with different symmetries, or they just live inside some symmetry broken state. They never live just outside, sort of inside the symmetric phase, far away from any phase boundary. Okay, of course, there are many ways to interpret that, but that's an experimental fact, I believe. Okay, so there's another interesting characteristic which is common to all of these superconductors as far as I could tell, which is that they're always in the so-called clean limit. Okay, so the clean limit means that the mean free path of electrons in the system at low temperature is larger than the superconducting coherence length estimated from the out-of-plane critical field. Okay, and the mean free path is usually very, very large at low temperature. It's of the order of the system size, in fact, a few microns. And the coherence length can vary, but it's tens to a few hundreds of nanometers. So we're really deep in the clean limit. Okay, and why is that important? Okay, so disorder can have an effect on superconductors, as you know. If you have non-magnetic disorder, that is not expected to affect Tc in an S-wave superconductor, but it suppresses Tc very rapidly in anything but S-wave superconductors. Okay, and that's the fact that this is so deep in the clean limit means that non-S-wave or unconventional superconductivity is not ruled out, is not out of the game from step one in this system. Okay, and the most beautiful example that I know of this is what happens in strontium ruthenate, where early on there was this beautiful experiment where they just introduce, so they noticed that different samples have a different Tc, and they managed to introduce disorder in a very, very controlled way. Okay, so that varies the normal state residual resistance. So each point here is a different sample with a different degree of disorder, and this is Tc. And it just, so this is a non-magnetic disorder. They introduce impurities with no spin. And this is Tc as a function of the residual resistance. And it just follows beautifully this Abrikosov-Gorkov theory. Okay, so in particular, there's a critical amount of disorder, which is quite low, where superconductivity is killed, and that corresponds to a mean free path of the order of the coherence length of the clean system. Okay, so this is what you would expect in a non-S wave, and unconventional superconductors don't have a dirty limit. If the coherence length is shorter than if the mean free path is shorter than coherence length, superconductivity should just disappear. And this is not the case in these systems. Okay, so yeah. So these are some properties of these superconductors. Okay, any questions so far? All right. So what I'd like to discuss a little bit, of course, what we would like to know is why is there superconductivity in this kind of system? What is the symmetry of the order parameter? What's the pairing glue, and so on? Okay, so this is a very, very unusual regime to find superconductivity in, and I think this is one of the reasons this is interesting. Okay, remember the electron density is extremely small. This is sort of all the parameters of the system are sort of in the opposite regime than what you were used to in a conventional superconductor like lead or aluminum. The density of electrons is tiny. The Fermi energy is actually very, very small. The Fermi energy is just a few millivolts compared to the phonon frequency, for instance. So depending on which phonons you choose, the phonon frequency is definitely not low compared to the Fermi energy. So all the usual inequalities that exist in a superconductor are sort of reversed. But nevertheless, sort of a natural hypothesis is that a superconductivity is just coming from the lowest available frequency, lowest frequency of phonons that are available, and these are the acoustic phonons. Okay, so in-plane acoustic phonons. In graphene, these are reasonably strongly coupled, and the idea is that these are responsible for superconductivity in this system. Okay, so there are a few reasons to think that this might not be true, and even though I think the jury is still out, I think we don't know the answer yet. But let me present the arguments. Okay, so the first argument is just what I just said before. Okay, if you think about the characteristic frequency of these phonons, of the acoustic phonons. Okay, so acoustic phonons are gapless. Their frequency goes all the way to 0 at q equals 0. But the important phonons for pairing would be phonons where q, the wave vector of the phonon, is of the order of kf or 2kf. Okay, so these phonons can connect electronic states on the Fermi surface. So an important frequency scale in the problem is the so-called Bloch-Gruneisen temperature, which is just twice the speed of sound of the phonons times kf of the electrons. Okay, so this is the frequency of the phonon that connects electrons from one side of the Fermi surface to the other side. Now, this frequency is not a small fraction of the Fermi energy in this system. It's actually of the same order. It's maybe half of the Fermi energy. So again, there's no room for retarded interactions in the system. There isn't this usual separation between the Fermi energy and the phonon frequency, even for the lowest frequency phonons. And this is because it's graphene, so Vs is very high. Okay, the speed of sound in graphene is extremely stiff in the plane. Okay, so that's that's one special thing about the superconductor that makes it not so easy to understand how these phonons can pair. But there's a more serious issue, which is the normal state resistance in the system. So usually what you would expect if you have strong coupling to this kind of phonon, when the temperature reaches some fraction of this Bloch-Gruneisen temperature, the phonons would be excited and they would start scattering the electrons, and that would lead to a linear T resistance. Okay, so this is the classic Bloch-Gruneisen plot. So this is temperature over this frequency scale. This is resistivity. Okay, and in the normal state, so when the temperature exceeds, say, a fifth of theta Bg, okay, which in the system should be around maybe 20 Kelvin. You should see a linear in T resistance, and the slope of the resistance is just proportional to lambda, which is the dimensionless electron-phonon coupling in the system. Now, this type of behavior is actually seen in these systems, okay, and we can try to estimate what the slope is, and knowing or estimating the different Fermi energies of the different pockets of electrons, we can infer a value for the electron-phonon coupling constant lambda, okay, through this formula, and the slope that is observed experimentally is maybe 1 or 2 ohms per Kelvin. And from that, you can try to estimate the lambda. Of course, there's some uncertainty as to which Fermi energy you're supposed to use. Presumably, at this temperature range, interaction effects are not going to renormalize the masses so strongly. So we can use sort of a bare mass. And if you do that, you get the value of lambda, which is very, very small. Okay, so the electron-phonon coupling constant inferred in this way would be small. Now, it's essentially the same lambda that would go into the BCS formula for TC. Okay, so it looks like a coupling to acoustic phonons in the system is just too small. Okay, so if it's not phonons, then what is it? Okay, so this, okay, let me just mention, okay, so there are 2 electron-phonon coupling constants here, lambda and lambda SC. Okay, they just correspond to different Fermi surface averages. So lambda is the effective coupling constant that goes into transport. Lambda SC is the coupling constant of superconductivity. In normal metals, these 2 numbers are usually the same within maybe 30%. Okay, so if lambda is so tiny, then we think that lambda SC is small as well. Okay, so from now on, I'm going to talk about theory a little bit. So this let us think about non-electronic mechanisms. And of course, we know of several possible mechanisms for superconductivity that occur purely out of repulsive interactions between electrons. Okay, so this it goes back to the famous work by Kohn and Luttinger. Okay, so what happens is that the Coulomb interaction between electrons is dressed, is screened by the interaction between every pair of electrons is screened by all the other electrons. And this effective screen interaction can actually have an attractive part, in particular for for anything but simple S-wave pairing. Okay, and we also thought about a related but different mechanism for superconductivity, which is we saw that at least some of these superconductors occur right at the boundary between 2 phases. One of them is symmetry broken, and the other one is asymmetric. So you could imagine that it's the fluctuations of the nearby ordered phase are mediating pairing between electrons. Okay, so we looked at fluctuations of a particular ordered phase which exists in this system, which are so-called the IVC, or inter-valley coherent pairing, inter-valley coherent order. Okay, so we saw that yesterday. It's a state where you spontaneously create a coherent superposition of the 2 valleys. In real space, it's some kind of density wave. And fluctuations of that kind of order parameter can also lead to pairing. Okay, interestingly, actually, these 2 mechanisms actually result in the same symmetry of the order parameter, which is this chiral p-wave-like order parameter. Okay, so it's a state that breaks time reversal symmetry spontaneously within each one of the valleys. The superconducting order parameter has this phase winding around the Fermi surface. This is something very generic. Okay, if you have superconductivity arising out of repulsive interactions, what you often get is that the phase of the order parameter changes over the Fermi surface in some way. Okay, it either changes in this continuous way, or there's an opposite phase between the 2 parts of the Fermi surface, the inner and the outer. This is this annular Fermi surface that we saw before. Or the phase jumps somewhere on the Fermi surface because the order parameter goes to 0, like in a D-wave superconductor. Okay, so this is a feature that you would expect if this is the right mechanism. Question, yeah.
These are purely electronic mechanisms.
Yes, yeah.
Mentioned in this system, the sensitivity always often they very close to a symmetry.
Yeah.
Countering.
Yes.
Suppose you have a symmetry working state, then the other neutral.
Yeah.
Are they?
Yeah. So so this is this mechanism. Okay. So that I count as a purely electronic mechanism. Okay. So
YBC is basically
electronic, yes. There's a neutral mode, but it's not an external mode. It's a mode of the SECT electrons that they're pairing. Okay, so it's all coming from the Coulomb interaction ultimately. Okay, so this I still count as a purely electronic mechanism. No. Yeah, that's important. Okay, so the story is this, right? So we have a tiny electronic density and no Moiré lattice. So you can really think about the system as a continuum. Okay, now you can have very strong electron-electron interactions. We know that the electron-electron interactions have to be very strong, because if they weren't strong, we wouldn't get all these symmetry broken states in the first place. Okay, but these electron-electron interactions would not show up in the resistivity. And the reason is momentum conservation. Okay, so you have electrons interacting with each other, they scatter each other very strongly, but the total momentum of the system is conserved, so they don't affect the DC conductivity at all. Okay, so but this is actually a feature, not a bug, because the linear resistivity, we believe, might as well come from phonons, and the slope is very small. Okay, so that's okay. Yeah, okay, so this is exactly this point. Okay, so electron-electron scattering conserves momentum. Doesn't matter in what way what other ways it affects the system, for instance, creates these collective modes and so on, but it shouldn't show up in the resistivity in the system. By the way, this is because of the absence of a superlattice. Okay, this argument does not work for instance, twisted bilayer graphene, where there is a Moiré lattice that can cause umklapp scattering. Okay, but there's no such thing here. Yeah, so this is an important point. All right, so so let me dive a little bit deeper into these different mechanisms. Okay, so the Cohen-Luttinger mechanism that was mentioned yesterday. Okay, so the idea is you take fermions with repulsive interactions. At lowest order, you have a repulsive vertex that does not lead to any pairing, but in the weak interaction limit, where you can actually perform this calculation, you just go to the next order. You address this interaction by these terms, and it turns out that the interaction that you get can actually be attractive in a non-S wave channel. Okay, so it turns out that in two spatial dimensions, there's something special about this mechanism. This mechanism actually does not work very well for a parabolic dispersion, for electrons with a purely parabolic dispersion. The reason is you see that this effective interaction to second order in the Bayer interaction actually contains this polarization bubble. This is just the Linhart function of electrons, the susceptibility. And as you may know, at zero frequency, the Linhart function in two spatial dimensions has a special feature. It's actually completely flat. It's constant all the way from zero momentum up to 2kF. Okay, that's really a very special thing about parabolic dispersions in two dimensions. Okay, and since the polarization is constant as a function of momentum, it would also lead to an effective interaction, which is constant as a function of momentum. And that means that this interaction is going to be repulsive in all channels. Okay, but this feature goes away immediately once you violate this parabolic condition. Okay, so you go to anything but parabolic dispersion. If you have multiple subbands, or if you have trigonal warping, the polarization function would become more structured, and you can get non-trivial solutions to the gap equation. Okay, so we've done some calculations along these lines. So let me describe briefly what the calculations are. Okay, so interestingly, in ABC graphene, the superconductivity, both SC1 and SC2, occurs in this regime where the Fermi surface has these two components. It's this a Mexican hat, inverted Mexican hat type dispersion. So there's an outer Fermi surface of holes, an inner Fermi surface of electrons. So the Fermi surface is an annulus. Okay, so that has an interesting structure to the polarization function, which is exactly what we want in order to get pairing. In particular, the polarization function is peaked at wave vectors that correspond to a wave vector that corresponds to the separation between the inner and the outer Fermi surface. Now, the simplest thing we can do is treat the screening within the RPA approximation. Okay, so we're in a metal, so the interaction between electrons is going to be screened by all the other electrons, and we get this RPA form of the effective interaction. N here is the number of fermion flavors, it's 4 in the symmetric state. Okay, and then what we can do is just, instead of using the bare interaction, which is Coulomb, we use the screen interaction and try to find solutions to the gap equation using that. Okay, and the interesting thing, so this is what the screen interaction looks like in momentum space, but this is what it looks like in real space. So V naught here is just 1 over R, Coulomb. Okay, so that's the Fourier transform of this bare interaction. And V of R is the screened Coulomb interaction, including this RPA screening, and it has these so-called Friedel oscillations, okay, coming from the characteristic wave vectors of this problem, which are differences between the inner and outer Fermi radius. Okay, and it starts with a repulsive core, but you see that there's a range of distances where the interaction actually becomes attractive. This is what would cause pairing. Okay, so now we've done slightly more realistic modeling of the system, including trigonal warping and so on. So our Hamiltonian is very simple. It's just this dispersion, including the wave functions. Okay, as was also mentioned yesterday, the form factors of the interaction also come into this calculation. These bands have a Berg curvature in them, plus Coulomb interactions. And the Coulomb interactions are actually screened by the nearby gates. Okay, so that's taken into account. D is the distance to the top and bottom gates. Okay, and this is essentially what we do. We just simply dress this interaction using RPA. The number of flavors can be either 2 or 4, depending on whether we are in the symmetric phase or the half metals phase, where only 2 of the flavors are occupied. Now, you can ask, when is this calculation actually justified? Okay, so after all, we are dealing with a strongly interacting system. And this is a somewhat crude approximation. It is crude. There's one limit in which this calculation can be actually controlled, where this is actually the correct, we know what we're doing, this is the correct thing to do, which is when the number of fermion flavors, if we treat that as a parameter, if that number is large. Okay, so our expansion parameters are really 1 over 4 or 1 over 2. Okay, not the greatest expansion parameter, but we work with what we have. So at least what I'm going to show you is the correct answer for some system, maybe not quite rhombohedral multilayer graphene. Okay, but with that caveat, we do the calculation. This is what the polarization function looks like for this system, including trigonal warping. The important feature is that it's larger, close to Q equals 0 over some range, compared to Q of order the 2kF of the outer Fermi surface, which is out here. Okay, so and then we just use this effective interaction as usual in the pairing channel and solve the gap equation. Okay, and what we get is an effective dimensionless coupling, BCS coupling. Okay, sorry, it's also, I also called it lambda. It has nothing to do with phonons. It's all from electron-electron interactions. And so that's the number that would go into the exponent of the BCS formula. And there's a prefactor that we have to put in. For the electron phonon problem, that would be the phonon frequency. Okay, but here there are no phonons, so we use the Fermi energy as our scale. Okay, and this is lambda. So this is lambda as a function of density for ABC rhombohedral graphene using this mechanism. Okay, so it does something interesting. Okay, so you see that out here, when the whole density is large, this is where you have a singly connected Fermi surface. Lambda is very, very small. So TC is exponentially small, so it's essentially zero. Something happens when you nucleate this inner pocket. Okay, so lambda jumps. It's still very, very small, but it has this jump. Okay, and then it increases monotonically as the outer Fermi surface shrinks and the inner Fermi surface expands. Okay, and this sharp peak over here is the Van Hove singularity. This is where they meet each other. There's a singularity of the density of states, and hence there's a large peak in TC. Okay, so you can get values of lambda of maybe 0.2. Okay, depending, of course, on where you are. If you're really close to this Van Hove singularity, this theory doesn't work anymore. So you should cut it off somewhere. But you can get reasonable numbers of lambda that can explain the observed TC. Okay, and it's interesting that you don't actually need this angular structure. You go to the other side of the Van Hove singularity, you have these three pockets, but lambda is still substantial on the other side. The only thing that you need is to be as far away as possible from the simple parabolic singly connected Fermi surface limit. That's very bad. Okay, so yeah. So the symmetry of the order parameter that you get from this particular mechanism, as I mentioned before, is this chiral P wave. Okay, so what I mean by chiral P wave is really that under a C3 rotation of the system, which is a symmetry of the crystal, this order parameter picks up a phase of plus or minus 2 pi over 3. Okay, so it has angular momentum plus or minus 1. And if you go beyond the linearized level, this is actually a chiral P wave. This would break a time reversal symmetry spontaneously. Okay, I'm almost out of time. Yeah, let me just say a few more comments and then I'll finish. Okay, so first of all, an interesting question is theoretically, is this actually a topological superconductor? Okay, so you know that a chiral P wave in a singly connected Fermi surface would be topological. It would have chiral edge states and so on. Is this type of superconductor that we predicted here topological? So it turns out that it isn't. The reason it isn't is that the structure of the Fermi surface, it has this hole pocket and a electron pocket in each valley. The Chern numbers from these two pockets actually cancel each other. Okay, so the total Chern number of the superconducting state is actually 0. Now, because of that, we're actually motivated to look at different numbers of layers and different stackings. So we considered a bilayer graphene, trilayer graphene ABA, ABC, four-layer graphenes ABAB and ABCA. Okay, we just ran the same mechanism for all of these systems. Not very surprisingly, it turns out that the best system for superconductivity is the four-layer rhombohedral system. And it turns out that in that system, you can actually get, theoretically, you can get superconductivity in a range of parameters where there's a very trigonally warped, but singly connected Fermi surface in each valley. So this is actually predicted to be a topological superconductor. We can claim that we predicted superconductivity in ABCA graphene, but that's of course not a huge surprise once we knew about superconductivity in ABC. Okay, so superconductivity was indeed observed in ABCA graphene and actually any number of layers, 2 or larger. Yeah, so are there any questions? basically out of time. Let me see if there's just one more thing I want to say. Yeah, maybe not. Maybe I'll just finish there. Yeah, I'll just go here. Okay, so yeah, so just to conclude, view. So I think these are very, very interesting superconductors. There are reasons, there are at least good reasons to think that they're not conventional superconductors. Jury is still out. I think to devise the right experiment to tell, it turns out extremely hard to tell what the symmetry of the order parameter, which is also the most interesting question. Let me mention also one of the biggest surprises that came out recently in this system is the following. So the most natural thing to think about in these systems is pairing of electrons between the two valleys, of course. Okay, so whether it's singlet or triplet, you can always pair an electron from valley K with an electron from valley K prime. They are time-reversed pairs. But it turns out that in 4, 5, and 6 layers, you can actually get superconductivity in regions of the phase diagram where there's only one valley present in the Fermi surface. Okay, so that suggests that actually pairing occurs within electrons in the same valley, which is an extremely surprising result. That kind of superconductor almost has to be unconventional. It has to be P-wave because there's only one flavor of electrons. So all these things support the idea that this is not a conventional phonon-mediated superconductor. Okay, let me finish there. Thanks.
Does anyone have any questions?
Thank you for the very nice talk. So I guess one thing you have identified, or is also known, is like a large density of states is often helpful for superconductivity, but it can also be helpful for these like spontaneous symmetry broken phases.
Yes.
Is there any big picture that you've learned, maybe as also that could be applied to like bulk crystals for when is a system going to prefer to just order versus go superconducting?
Yeah. That's a very interesting question. So yeah. So the one thing we think we understand theoretically is that what you said is completely correct. Okay, so high density of states helps both superconductivity and all these other the other states. The difference is that superconductivity doesn't care where that high density of states is coming from. When you have a peak in the density of states, it's always good for superconductivity. At least of the conventional kind, between time-reversed states, because you always can find time-reversed states on the Fermi surface. On the other hand, if you have all these other competing states, they care about how exactly the Fermi surface looks. Okay, so how the, not necessarily the Fermi surface, but how the electronic dispersion looks. It turns out that this particular dispersion with sort of a very flat region and then a very dispersive region, that's very good for these generalized ferromagnets. It turns out, among all the possible states. And the reason is it's a direct analog with quantum Hall ferromagnets. Okay, so quantum Hall ferromagnets occur in a completely flat band. If you only occupy the bottom of this, the flat region of this band, it sort of looks like a generalized quantum Hall ferromagnet. So this might explain why these sort of itinerant ferromagnets are so prevalent in the system and are so rare, quite rare in general.
Hi, thank you. Thank you. Very nice talk. I have a question about the Cohn-Ledinger story.
Yeah.
This part of the question is about 80% redundant with Yonglong's question, but given that the superconductivity experimentally sits close to these symmetry broken phases, why wouldn't we kind of naturally expect a fluctuation exchange mediated?
Yeah. So it's a great question. So the fact that superconductivity lives at the border of another symmetry broken phase, there are two ways to understand that, and I don't think we know which way is correct. one way is to say exactly what you said, to say, oh, there are fluctuations of the nearby phase. They can mediate superconductivity. We know of many ways that can happen. But there's another way that has nothing to do with fluctuations of the nearby phase, which is simply to say, well, the density of states is growing as we approach some special density, say some Van Hove singularity. It's growing. TC is going to grow exponentially. But at some point, the density of states is so high that you're going to satisfy the Stoner criterion, and the system is just going to break the symmetry and lower the density of states. Okay, so the second possibility can work for any mechanism. It can work for electron phonon. It can work for this Cohn-Luttinger. Okay, so yeah, so that's always a dilemma when thinking about these systems. Let me also mention that at least some of these electronic phase transitions between symmetry broken states are first order.
Okay, thank you. So if both Cohn-Luttinger and this, fluctuation exchange can produce unconventional pairing, is there any, I mean, this is not a very fair question, I admit, but is there any experimentally observable thing that can distinguish them?
There is, yeah. So if there are some kind of low energy fluctuations strongly coupled to the electrons, you should see them in other probes. Okay, but at this point, I think that's, in my view, that's the least of our problems. We want to know, is it just boring S wave or something else?
Thank you.
Yeah.
I may want to, thank you for the talk. I may want to follow up on the previous question. So traditionally, it's considered that Cohn-Luttinger would give you a transition temperature that's kind of
low,
exponentially suppressed by the angular momentum of pairing.
Yeah.
So is there like any qualitative estimations that why in this case it's much larger?
Yeah. So there is. Let me make two comments about that. So indeed, the TC is exponentially small in the angular momentum. That's why the angular momentum of the states that we find is never bigger than 1. Okay, so now, okay, there was some caveats. In the system has trigonal warping, so there really isn't an angular momentum bigger than 1. But the winding of the order parameter around the Fermi surface is only 1. Okay, now the other comment is that these anisotropic Fermi surfaces and multiple pockets and so on are the crucial ingredient. Okay, the fact that you get the TC, which is extremely small, okay, meaning exponent of some minus some very large number, that really is a property of simple parabolic dispersion. Okay, all these multiple pockets, which by the way occur in all of these superconductors, the dispersion itself is different, but it's always complicated. That's crucial. That's comment number 2. Comment number 3 is that is an anecdote. In the original Cohn-Luttinger paper, they were actually thinking about helium-3. And they tried to estimate what the TC should be. For some reason, they started from L equals 2. If they just put their L equals 1, they would get the number that's not so off. Okay, so this is somewhat of a preconception, I think, which is not quite justified. Okay.
Okay, let's thanks Professor Berg again.
Thanks.